myself Shweta Shah. I am an instructor for the subject Computer Organization and Architecture. In this subject we have started Unit 4, that is Microprograme Control. In this unit we are going to see today the topic that is Microinstruction Format and the Microprogram Sequencer. So let me start with the first topic, that is Microinstruction Format. The microinstruction format for the control memory can be given like this. It is consisting of the 5 fields, that is F1, F2, F3, that represents your operation or you can say micro operation, and each field is consisting of the 3 bit. Then second field is a DR CD field, that is of 2 bit. Then next field is a BR field, that is of 2 bit, and last one is a AD field, that is of 7 bit. Here F1, F2, F3 represents the micro operation field that will define which micro operation is going to be performed. CD represents the condition for the branching. BR represents the branching field, and AD represents the address field. Okay, so this 20 bits of microinstruction can be divided into 4 functional parts. First part is a 3 fields of F1, F2, F3 that specifies the micro operation for the computer. The micro operations are subdivided into 3 fields of a 3 bit in each, and these 3 bits in each field encoded to specify total 7 distinct micro operations, and this gives total 21 micro operations. 7 multiplied by 3, that means total 21 micro operations can be performed by using this F1, F2 and F3. A CD field selects the status bit or you can say condition for the branch. The BR field specifies the type of branch to be used, and the AD field contains the branch address. The address field is of 7 bit since the control memory has a total 128, that is equals to 2 raised to 7 words. So we can say that total instruction format is of 20 bit. Let me further see the example. An example, let me consider the micro instruction that specifies the 2 simultaneous micro operation from F2 and F3 and none operation from the F1. Okay, for example, F2 specifies the operation of transferring the memory content of address location given by the address register to the data register, and we can specify this by F2 as a bit pattern of 1 0 0. And second operation let me consider is of incrementing the program counter by 1, and if we can represent this by a sequence of 1 0 1 operation, that means our F2 will contain 1 0 0 to specify the transfer operation, and F3 will specify 1 0 1 to increment the content of program counter by 1, and our F1 will be 0 0 0 because it is not specifying any operation. So our 9 bits pattern will be like 0 0 0, then F2 for 1 0 0 and F3 as a 1 0 1. So our 9 bits pattern will be like this. The CD or you can say condition field is consisting of the 2 bit which encoded to specify the status bit condition, and this can be of anything like this. If its content is like 0 0, then unconditional branching, that means always have to do branching. If its content is 0 1, then your condition is D5 bit is 50, D5 bit is 1, that means your I bit is 1, that means you have used the indirect addressing, and then and only then the branching will be done depending upon this condition, whether you have to do unconditional branching or conditional branching or direct branching or what. Okay, if the content of CD is 1 0, then it will check for the accumulator's sign. That means it will show the see the sign bit of the accumulator's content. If it is 1, then only it will shift, otherwise no, and likewise. For last condition, that CD content is 1 1, that time it will check for the accumulator's content as a 0. If it is 0, then the branching will be taken. If you require to execute your instruction, you can use any of this condition. Okay, so by using this 2 bits condition, you can decide the branching, when you will do the branching. Okay, the third thing we have used here is a branch field. This field is consisting of the 2 bit and it is used in conjunction with the address field AD to choose the address of the next micro instruction as shown over here. If it is 0 0, then it will use the jump If it is 0 1, it use the call. If it is 1 0, then it will use the return instruction, and if it is 1 1, then it will use the map instruction. In JMP instruction, the address field AD field is used in the CAR register, that is your direct address. Okay, and the next time your content address register is incremented by 1. If it is 0 1, then the address register's content is directly used, but and also the this incremented value is also stored in the SBR register also. Okay, if the condition is 1, and if it is 0, then the content of the address register CAR is incremented by 1. Okay, in the next condition, if it is 1 0, then SPR's content is going to be stored into CAR. Okay, that means your it is written from the subroutine. Okay, and if it is 1 1, then it will use the mapping procedure that we have already learned, that it will use the 4 bits, and for the MSB and the last 2 bit it will append 0. Okay, so from any of this 4 method, it will decide how it has used its address field. Okay, so by this way, by combining this 5 bit, that is your F1, F2 and F3, that is for your operation, then combining this with BR field, CD field that shows your status, BR field that shows how you are to access the address, and AD field, that is your address field, you can find out what is your micro instruction, how you have represented your micro instruction. Okay, next we will see the microprogram sequencer for your control memory. The basic component for the microprogram control unit are the control memory and the circuit that selects the next address. The address select part is called as a microprogram sequencer. A microprogram sequencer can be constructed with the digital function to suit a particular application. To guarantee a wide range of acceptability, an integrated circuit sequencer must provide an internal organization that can be adapted to a wide range of applications. The purpose of the microprogram sequencer is to represent the address to the control memory so that the micro instruction can be read and be executed. The commercial sequencer include within the unit in an internal register stack used for the temporary storage of the address during the microprogram looping and the subroutine and call. Some sequencer provides an output register which can be function as an address register for the control memory. These both things can be possible. The block diagram for the microprogram sequencer is shown over here in this figure. This is consisting of the 2 multiplexer, CAR register, incremental SBR register, and for the input logic and your control memory. Okay. Here control memory is also consisting of the 20 bits and having total 128 locations to store. Okay, because our instruction is of 20 bit, so it will have word length of a 20 and having total 128 locations. Here there are 2 multiplexers and in the circuit, this first multiplexer selects the address from the one of the 4 sources and routes it into the control address register, and the second multiplexer takes the value of the selected status bit and the result of the test is applied to the input logic circuit. The output of the CAR provides the address for the control memory. The content of CAR is incremented and applied to one of the multiplexer input and to the subroutine register, that is SBR. The other 3 inputs to the multiplexer, one comes from the address field of the present micro instruction, second is from the output of the SBR, and third is from the external source that maps the instruction. So total 4 inputs are possible for your mux 1 and that are given like this. Next we can say here we have seen this multiplexer 1 is having 4 input and that can be given like this, and your multiplexer 2's output is provided for the input logic to decide how your input is generated. Although this figure shows the single subroutine register, a typical sequencer will have a register stack about 4 to 8 level deep. That means it can have a 4 to 8 sequence register. In this way, the number of subroutine can be activated at the same time. So the CD condition field in micro instruction selects the one of the status bit in the second multiplexer. If the bit selected is equal to 1, the taste T variable is equals to 1, otherwise it is equal to 0. The T value together with the 2 bits from the BR field goes into the input logic circuit, and that will decide how your input is accessed. The input logic in particular sequencer will determine the type of operation that are available in this unit. A typical sequence operation are increment, branch or jump, call and return from the subroutine, load an external address, push or pop the stack, and other address sequencing operation that we have already seen in the DR. Okay. Next thing we can say that with 3 input the sequencer can provide up to 8 address sequencing operation. Okay, so 8 different operation for your address sequencing can be possible. Some commercial sequencer have 3 or 4 input in addition to the T input, and thus provide a wide range of operation for selecting the input. So by this way we can use your microprogram sequencer for your control memory. So we are ending our today's session over here. If you have any question, then you can contact me.